Our first problem on the study guide, Cindy had 3 consecutive even integers. Even integers have a +2 pattern. So as soon as I see 3 consecutive even integers, I always start off with the first integer being some variable. I like to use n. Then we just apply the pattern to n. So n, add 2, we get n plus 2. Add 2 to that, we get n plus 4. So those would be the 3 consecutive integers algebraically using the same letter to represent each. First, second, third. She found that the sum of the integers, so if we add up all the integers, that's the first integer plus the second integer plus the third integer, was 48, means equals 48. So it gives us the ability to set it up just like that. And then if I just were to combine like terms, we're going to get 3n plus 6 is equal to 48. Move the 6 over here to get the variable number separated. So 3n on the left by itself now is equal to 42. Divide by 3, we get n is equal to 14. n represents the first integer, then I have to add 2 and 4 to get the next 2. So the final answer should be 3 integers, 14, add 2 to get 16, add 2 to that to get 18. So 3 consecutive even integers, add them up, you get 48 if you try it out. Number 2, a fair coin is tossed 6 times. What's the probability that comes up heads every time? So we're looking for 6 heads in a row. Each probability of a head is a half. So that's the first flip, second flip, third flip, fourth flip, fifth flip, and sixth flip. And when you do multiple flips, you simply multiply each probability together to get the overall probability of the occurrence of that exact outcome, which is 6 heads. 1 on top, 1 times a bunch of 1s. 2 times 2 is 4, times 2 is 8, 16, 32, 64. So 1 out of 64 is the probability of getting 6 heads in a row. Fairies outnumber the hamadryads by 130%. If there were 690 fairies in the clearing, how many hamadryads were present? So it says outnumbered, which is a way of saying more. So 130% more. So if we're looking, it's like a before and after, but the hamadryads and the fairies, if we take a look, the fairies are the ones with the more percent, so the lesser percent, the before percent, is 100. And the fairies are 130% more than the hamadryad, so add 130 to 100, we get 230 for the percentage of the fairies. We know how many fairies there were, 690 for actual number, and we're looking for how many hamadryads were in the forest, or in the present. So if we just make this proportion 100 over 230 is equal to x over 690, cross multiply, 230x is equal to 69000. All we have to do then is divide by 230. $300 hamadryads, whatever they are. Number 4, simplify. We got some scientific notation looking stuff here. First thing I'm going to do is make everything into good scientific notation. So this number, I'm going to change that 0.04 into a 4. I made that 2 spaces bigger, so I make that 2 smaller. 8 minus 2 is equal to 6. This one here, 200,000, I'm going to change it to 2. I made it, it was here, I made it 1, 2, 3, 4, 5 spaces smaller. So we need to use a positive 5. We already started at 0, so we took 5 away, so we're going to add 5 to the power. On the bottom I got 20,000. Again, decimal point here, 1, 2, 3, 4 spaces over. Just like 200,000, 20,000 is made to be smaller here, so I have to make the power bigger, so 10 to the 4th power. And finally I got 0.000002. That's also a 2. 1, 2, 3, 4, 5, 6 spaces over to get where we need it to be, so times 10. I made that bigger by 6, so I have to make this smaller by 6, so -6. So that's priority 1, make everything good scientific notation. Then, multiply the tops. 4 times 2 is 8. 6 plus 5 is 11. On the bottom, 2 times 2 is 4. 4 plus -6 is -2. So, scientific notation on top and bottom. It doesn't matter so much about scientific notation here, as long as this divides easily, it's fine the way it is. So 8 divided by 4 makes 2. For the power of 10, my recommendation has been and always will be, write down the subtraction. It's top minus bottom. Actually, look at the subtraction you're doing. So top 11 minus bottom negative 2. Top minus bottom. Minus is plus, 11 plus 2 is 10 to the 13th power. Most common mistake, people see 11 or negative 2, they want to put 9. Again, the rule says to take top minus bottom, minus negative becomes plus. Once you transform it into what it really means, adding those is what's required. Same type of problem, so basically the same procedure. Scientific notation here, 5 times 10. 1, 2, 3, 4, 5, 6 spaces bigger, so 6 spaces smaller. Negative 43 is what we get for that one. 4,000 times 10 to the 5th. I'm going to move the decimal point right there. That's 4 times 10. 3 spaces smaller, so that's 3 bigger. 5 plus 3 is equal to 8. This right here, we got 2 times 10 to the, what's the 1, 2, 3, 4, 5 spaces bigger, so 5 smaller. And then finally we get 500,000. That's 5 times 10 to the something. Decimal points there, moves to here. 1, 2, 3, 4, 5 spaces smaller, so 5 bigger. So again, priority 1 is to make that happen. Second step, multiply. 5 times 4 is 20. And negative 43 plus 8 is negative 35. On the bottom, 2 times 5 is 10. And negative 5 plus 5 is 0. Okay, once again, neither one of these is good scientific notation, but what you have to worry about is that easy to divide? And 20 divided by 10 equals 2, so that's easy to divide. Go ahead and do it. It's not so important. They have scientific notation in this step as long as that's easy to do. And again, for the power of 10, I take top minus bottom. Negative 35 minus 0 is equal to negative 35. So that's the power of 10 that we're going to use for that one. So both of those, good scientific notation here. Multiply tops by multiplying abscissas, adding powers. Multiply abscissas, add powers on the bottom. Divide, subtract top minus bottom, and actually write it out on your paper so you can see what's supposed to be there. Number 6. I have that R sub s is equal to something else. I have that T sub s is equal to something else. And finally I have that T sub f is equal to something else. So my main equation, 3 of the 4 things in the main equation have a different structure. So if I go ahead and do all those substitutions, I'm going to keep R sub f exactly as it is, because nothing here says R sub f equals. I'm going to change T sub f into 5. Those are being multiplied, so these are being multiplied. Then I'm going to put an equal sign. And then I can see R sub s is equal to R sub f minus 3. I'm replacing one object with multiple objects, so parentheses are required. And finally, I'm going to change T sub s into 8. So times 8. This times this, this times this. So just like that, I've done all that substitution, and instead of having 4 different variables, I'm now down to one single type of variable. Now it's just a matter of solving that equation. So this multiplies through here. I'm going to get 5 times R sub f. I like the numbers in front, so that's not wrong, but just it's a better structure to have it that way. 8 times R sub f, and 8 times minus 3 is minus 24. If I move the 8 R sub f over to the left, I get negative 3 R sub f is equal to negative 24. I divide both sides by negative 3, we get R sub f equals 8. Once I know that R sub f equals 8, I go right there and I can see very clearly that 8 minus 3 is equal to R sub s. So 5 is equal to R sub s. So R sub f equals 8, R sub s equals 5. Both answers solved. Number 7, same type of problem. This time, if we take a look at what we know, R sub m equals something else. R sub r is equal to something else. T sub r is equal to something else. T sub m isn't, so it's going to stay as is. So if I start substituting what I know, R sub m is 10. That's being multiplied by T sub m. That's equal to R sub r, which is 6, which is being multiplied by T sub r, which is multiple objects, so parentheses, 8 minus T sub m. Once again, by doing that substitution, all 3 things, this, and this, into that equation, 4 variables, 1 variable, now it can be solved. Distributive property here gets me 10 T sub m on the left. Nothing happened to the left side. 6 times 8 is 48. 6 times negative t sub m is negative 6 t sub m. I'm going to move the t sub m to the left, so plus 6 t sub m. Move it across, it changes signs. Both positive, we add 16 t sub m is equal to 48. We divide both sides by 16, t sub m equals 3. T sub m is 3, so t sub r is equal to 8 minus 3. Just replacing that with a 3. So t sub r is equal to 5. Again, just like that, both things we don't know what they're asking us for are solved, so we're done. Number 8, solving a rational equation. We got numbers on the bottom. The least common denominator of the fractions is 10. So I'm going to multiply the entire equation by 10 to get rid of the fractions. It's divide first, then multiply. 10 divided by 2 is 5, times x is 5x. 10 divided by 5 is 2, times 3 plus x. So it's plus 2 times 3 plus x. And that's a binomial numerator, so that binomial is being multiplied by the quotient there. And 10 divided by 10 is 1, times 41 is 41. And just like that, there's no fractions. A simple little distributive property happening right here. So I get 5x plus 6 plus 2x is equal to 41. Slide the 6 over and change the sign. 7x is equal to 35. Divide both sides by 7, x equals 5 is the correct solution. Number 9, a fraction equation, this time with some mixed numbers. So the first thing I would do is rewrite it as 5x over 3 minus 17 over 5 is equal to 149/15. Okay. Multiply, add. So 1 times 3 is 3 plus 2 is 5 over 3. 3 times 5, 15 plus 2, 17 over 5. 9 times 15, 135 plus 14, 149 over 15. At this point, the least common denominator of everything is 15. Again, this is not a required step, but it sure makes the problem easier. It's worth doing. Divide, then multiply. 15 divided by 3 is 5, times 5x is 25x. 15 divided by 5 is 3, times negative 17 is negative 51. 15 divided by 15 is 1, times 149 is 149. 25x minus 51 equals 149. Move the 51 over, it becomes positive. 25x is equal to 200. Divide by 25, I get x equals 8. Number 10, factor completely. Notice the word completely here. That means always take out greatest common factor first, then multiply, then factor the leftovers. So A is every term. So if I take out A, what's left from the first term is x squared, second term plus 15x, last term plus 56. And I'm looking for my factors up chart, so factors of some number, which is positive 56, this number, whose sum is positive 15, which is that number. So once it's 1x squared, something x something, we want factors of the constant whose sum is the linear coefficient. And if you can find those numbers right off the bat, more power to you. If not, then kind of step your way up through it. 1 times 56, 2 times 28, 3 doesn't go into it, 4 times 14, and so on. But 7 times 8 is the correct pair. 7 times 8 is 56, 7 plus 8 is 15. So x plus 7 times x plus 8 is the factored form of all of that. The greatest common factor is part of the factored form, has to be brought down. Make sure that you do include the greatest common factor in your final answer. Number 11, same deal. We have a binomial this time. A plus b times x squared minus 4 times a plus b. They have a binomial common factor of a plus b. If I extract a plus b from that expression, what's left from the first term is x squared. What's left from the second term is minus 4. X squared minus 4 is a binomial difference of squares. X times x, 2 times 2 being subtracted. If you see a difference of squares, the factored form of the difference of squares is simply the square root of the front number in front, the square root of the back number in back, one positive, one negative to create the negative sign on that. And the outside product, negative 2x, and inside product, positive 2x, cancel, leaving getting rid of that x term. So that's why we just have a quadratic and a constant. There's no x term in the middle. But square root of that, 1 plus, 1 minus. And then once again, a plus b is the common factor. It is part of the solution. Make sure you include that in the factored form. Number 12. The easiest way to do it is with substitution. I can see that n sub n is equivalent to n sub d plus 1, so I can change this n sub n into n sub d plus 1. So 5 n sub d plus 1 plus 10 n sub d is equal to 110. You're welcome to call that n and d if you wish to. N, d, take your pick. I'll just go subscripted since I've already started that way. 5 times both of these things is going to give me 5 n sub d plus 5 plus 10 n sub d is equal to 110. I'll move the 5 over to the other side. Add together like terms. 15 n sub d is equal to 105. Divide both sides by 15. N sub d is equal to 7. Once you know that n sub d is equal to 7, n sub n is n sub d plus 1, so n sub n is n sub d plus 1. Instead of writing n sub d though, I wrote 7, and that means n sub n is equal to 8. We have a system of equations, just x's and y's. X object, y object equals number, so for both that's elimination is the easiest way to do this one. And this is even better because plus 2y and minus 2y are already opposite of each other. So I can just start by right away adding the equation together. 3x plus 5x is 8x, 2y minus 2y cancels, 10 plus 6 is 16, so x equals 2. Once I know that x equals 2, I can go back to any equation I want to. I like this one because everything's positive. It says 3x plus 2y equals 10, but instead of writing x, I know x equals 2. I can just substitute 2 there. So 6 plus 2y equals 10. Move the 6 over here, so 2y is equal to 4. Divide by 2, you get y equals 2. X and y in an ordered pair fashion. X goes first, y goes second. 2 comma 2 is the correct solution. Number 14, when you see negative powers or powers in general and there's a plus or minus sign involved, you have to treat that as everything's in its location, and you got to do it this way. So I'm going to put a fraction bar with a plus sign to represent the 3 pieces here. This piece is in the top left-hand corner over here, 1 over AB. Make it a fraction because that's what the negative powers do, but don't move them all the way to the bottom of the whole fraction, just make them a fraction in that location. AB is right here, so AB is going to stay right there, no negative powers to deal with, so it just stays AB. And then on the bottom I've got AB to the negative first power on the bottom, so 1 over AB to the first power on the bottom. So again, this belongs up here, make it a fraction. This belongs up here, make it a fraction if necessary, which it isn't. Make that a fraction in its location. Once you get to that point, then you just identify every object. And those objects that are fractions need to be fixed. So AB is the least common denominator of all the fractions. So times AB here, times AB here, and times AB here. Cancel what can cancel, and then leave the leftovers. So again, I'm going to create the same structure, something plus something over something. It's got to look like this. AB cancels AB, leaving me with 1. 1's on top, 1's on bottom. Top, top, everything here's on top, so A squared, B squared. There's no cancellation there because there's no fractions there, it's just straight multiplication. And then here, AB cancels AB, leaving me with a 1. So 1 plus A squared B squared over 1, or 1 plus A squared B squared over 1 can be ignored if you wish. I would take either one of these answers for that one. 15 is the same kind of problem, except instead of starting here, it already starts off in this structure. So you can see it already starts off in that whole fraction structure. So I've got a 3. I've got a 5 over x, I've got a 2 over x, and I've got a 4. The only two I have to really care about are the red and the green ones with the over x's, because they're the fractions. So I'm going to multiply everything times x, so times x, times x, times x, times x. And then here's my fraction bar, here's my plus, because that's the structure. Up in the top left, I'm multiplying 3 times x, which is just 3x. There's no fractions, so nothing happens, just straight multiplication. Up here on the top right, the x's cancel, so I get plus 5. Bottom left, the x's cancel, so I get positive 2. Bottom right, no fractions, so it's just multiplies, you get 4x. Once you get a simple fraction, you're done.